Welcome back. In this video, we continue our study of Chapter 1 and we move to Section 1.3 about multilinear bounded operators. Okay, let us first start with the case of bilinear operators, which just are functions of two variables. And then, if we understand this case, we can easily move to the general case of n variables. Okay, so what is a bilinear operator or bilinear map? If we have three vector spaces, E1, E2, and F, and we consider a function of two variables, so L is a function from the product space of E1 times E2, and that takes values into F. Okay, so we have a function of two variables. We say that this function is bilinear if it is linear in each variable separately. So if we fix one variable, we get a partial map, and this map is linear. Okay, so this means if we fix x2 and we let the first variable vary, so the image of a linear combination is a linear combination of the images provided we fix the second variable. And if we fix the first variable, we get a linear function in the second variable. Okay. So, but do not confuse a linear map of two variables with a bilinear map. So this is not, so a bilinear map is not a linear map in the couple. Okay, so for example, if we take E1 equal E2 equal F equal the space of continuous functions on 0, 1 that we encountered before, and we set L of U and V to be the product of the two functions, just the normal product. Of course, it's well defined because the product of two continuous functions is continuous. So L is a map from E1 times E2 into F. So it's a function of two variables. Now, as you may check, if we fix one variable, the partial map obtained is linear. Okay, as you may easily check. But this is not the same thing as saying that L is linear in the couple UV. Okay, so for example, L of the sum, so if I add to the couple UV another couple H1, H2, and we do the product, we get UV first component times second component, etc. So we get UV plus H1, H2 plus UH2 plus VH1. Whereas the sum of the couple, of the images of the couple, is just UV plus H1, H2. So L is not linear in the couple. Okay, this is very important. And also, if the image of a multiple of the couple, so L of alpha of UV will be just alpha square UV, as you know, whereas alpha of the image is just alpha UV. So when alpha is different from 1, these two are not the same. Okay, so do not confuse a bilinear map with a linear map of the couple. Okay, now since we'll be working usually in infinite dimensional spaces, continuity is not automatic. So we are interested in not just bilinear operators, but with continuous bilinear operators. Okay, so the first result is analogous to a result of the previous video, where we give several equivalent characterizations of continuity of a linear operator. So we will do something very similar here, but it's not completely equivalent to the continuity of a bilinear map. Okay, and just before doing that, remark, since, as you know, a linear map vanishes at 0, as you know. So therefore, if you have a bilinear map and we put one variable to be 0, then the result will be 0 because it's linear in each variable. Okay, and now we give several characterizations of continuity. So we have, suppose that now we equip the spaces, the vector spaces, with norms. So we have three norm spaces, and we have a function of two variables defined on E1 times E2, and we want to know when it is continuous. So, of course, we have to put a norm on the product. Now, we know that we can put several equivalent norms of the product, as we saw in the first video. Okay, one convenient norm is just the maximum of the norms of each component. Okay, but you can take the sum, or the Euclidean norm if you like, or the P norm. It's the same topology. So continuity doesn't change if I replace this norm by another equivalent norm. Okay, so the following conditions are equivalent for a bilinear map. L is continuous. Okay, now we can talk about continuity because these are topological spaces. So L is a map between two topological spaces, or just between two normal spaces. So L is continuous. Second condition, L is continuous at the origin. The origin is 0, 0, just denoted by 0. L maps bounded sets into bounded sets, so bounded sets of the product into bounded sets of the target space F. L is bounded on the unit ball of the product, the closed unit ball. And fifth condition, L is bounded on the unit sphere. Sixth condition, there exists a constant M such that the norm of the image of a couple is less than a constant times the product of the norms of each component. Okay, so this really looks like the properties of linear bounded operators of one variable. But here there is, if you observe, I didn't talk about Lipschitz continuity nor about uniform continuity. So in the previous video we had 8 equivalent conditions. Now we just have 6. So it's because it's not true. So Lipschitz continuity or uniform continuity is much stronger than these, because we shall see actually that continuity, the constant that we shall deal with continuity, it depends on the point, so cannot be chosen uniformly. Okay, so it's not true. Okay, because here we have 2 variables. Okay, so if you like, if we fix x1, we get a linear map, a linear bounded map in x2. So it's continuous in each variable. Okay, but the constant depends on the point. So if you consider L as a function of just x2, then the constant depends on x1, so it varies from point to point, so it cannot be chosen uniformly. Okay. Okay, so we'll do a circular proof, but observe that certain implications are trivial. So 1 implies 2 is trivial. 3 implies 4 is trivial, and 4 implies 5 is trivial. Okay, because the unit sphere is a part of the closed unit ball. Okay, here I should have put closed unit ball, but we can also put open unit ball, same thing, as you may check. So we have 3 trivial implications. So I will prove the remaining implications in a circular way. So first thing is 2 implies 3. Why? If L is continuous at the origin, then L maps bounded sets into bounded sets. Okay. So just write the condition of continuity of L at 0, 0. So what does it mean? It means that if x1, x2 minus 0, 0 is less norm than a certain number delta that depends on epsilon, then the distance between their images is less than epsilon. This is the condition of continuity. And now just take epsilon equal 1 and observe that L of 0 equals 0. So just have, as a particular case, if the distance between u1 and u2 minus the origin, the distance between u1, u2 and the origin is less than delta, then the distance between their images is less than epsilon. Here I take epsilon equal 1. So the delta usually depends on epsilon. Here I fix epsilon. So delta is fixed, is a constant now. So, and I will use this delta to prove the boundedness condition. So delta does not depend on u1, u2. It's constant. Okay. So this is continuity at 0. Now we want to prove what? We want to prove that L maps bounded sets into bounded sets. So take a bounded set A in the product, of course, and I want to prove that L of A is bounded. So which means that L of A is contained in a ball. Okay. So now if A is bounded, as we know, then A is contained in some ball of center 0. You can take any center if you like, but we can always put a bounded set into a ball of center the origin. Okay, so what does this mean? It means that if x1, x2 is in A, then the norm of x1, x2 is less or equal than r. And now I will prove that L of A is contained in a ball of center 0 and radius r square over delta square. So here these are constants. The r depends on the size of A, if you like, and the delta is a constant. Now, of course, don't confuse. This B prime 0 r is a ball in the source space, which is E1 times E2. And this ball is in the target space, which is F. Okay, so they don't live in the same space. Now, how do I prove that L of A is contained in this ball? It's equivalent to prove that the norm of L of x1, x2 is less than the radius, which is R2 over delta 2 for any x1, x2 in A. Okay, so this is the boundedness condition. Okay, now this is really trivial. You just apply this condition 1. So take an arbitrary point x1, x2 in A, okay, which is a bound set in E1 times E2. Then, as we said, the norm of x1 of the couple x1, x2 is less than r. And now take Q1 to be delta over R x1, so a multiple of x. So U1, U2 is the homothetic of x1, x2 with the ratio of center 0 and radius delta over R. Then, if you take the norm of U1, you will get delta over R times the norm of x1. And now, by assumption, the norm of x1, x2 is less than r, but the norm of the couple is just the maximum of the norm of x1 and the norm of x2. So the norm of x1 is less or equal than r. So the norm of x1 over r is less than 1. And same thing for the norm of x2 over r. So when I multiply by delta, I get something less or equal than delta. Okay. So therefore, since I'm taking the maximum norm of the product, because it's very convenient, we have that the norm of the couple, U1, U2, which is the maximum between the norms, is less or equal than delta. So we can apply, so the image of U1, U2 under L is less or equal than 1. And now I replace U1, U2 by their values. So I get L of delta over R x1, delta over R x2, norm is less than. And now I use the linearity of L, or precisely the homogeneity of L, because if I fix this, I can put the first delta over R outside L because it's linear in the first variable. And then I do the same thing with respect to the second variable. So I can put the other delta over R outside L. So I get delta over R times itself. And this is a constant, so I can put it outside. This is a scalar, so I can put it outside the norm. So here I'm using the homogeneity of L and the homogeneity of the norm. So I get delta square over R square times the norm of L x1, x2 is less than 1. And then when I multiply by the inverse, I get that the norm of L1 of L x1, x2 is less than R square over delta square. And that's it. So this means that the image of A under L is contained in the ball of center 0 and the radius R square over delta square. Okay, so this finishes the proof of the implication 2 implies 3. Okay, now as we said, 3 implies 4, 4 implies 5, and 5 implies 6. Okay, so where does this constant come from? We know that L, so assumption 5 tells me that L is bounded on the unit sphere. So that means that the image of the unit sphere is contained in some ball of center 0 and radius m. So the boundedness condition on the unit sphere tells me that there exists a certain constant m such that the norm of Lx1, x2 is less than m or equal for every x1, x2 in the unit sphere of E1 times E2. And now I want to prove, so this m will do, so I want to prove that Lx1, x2 for any x1, x2 is less than m times the norm of x1 times the norm of x2. This is the inequality in 6. Okay? So the same constant would do. So now take an arbitrary point in the product. So x1, x2. Now they are arbitrary. If one of them is 0, then the image of x1, x2 is 0 because by linearity. And the inequality in equation 6 tells me I have 0 less or equal than 0, so it's satisfied. Okay, so L of the image of the couple is 0, and the product of the norms is 0. So therefore, we assume that none of them is 0, so I can divide by their norms. And I take U1 to be x1 over its norm. So U1 is an element of the unit sphere of E1, and U2 is also an element of the unit sphere of E2. And therefore, according to my condition of boundedness on the unit sphere, the image under L of U1, U2 is less than, norm is less than M. And now again, I just replace U1 and U2 by their values and use once again the homogeneity of L and the homogeneity of the norm. So I can put the constant, the scalars, 1 over norm of x1, 1 norms over x2 outside L, and then outside the norm. And then I multiply by norm x1 times norm x2, and I get the result. So just same argument. So the same M. So M is actually can be taken to be the maximum or the supremum, precisely, over the unit sphere. So this concludes the proof of the implication 5 implies 6. Okay, now 6 implies 1, and we are done. Okay, this is a little bit harder than the other implications. Okay, so I want to prove now continuity at every point. So I fix an element, an arbitrary element x in the couple, in the product. So x is just x1, x2. And I want to prove what? I want to prove that L is continuous at x. So what does this mean? This means that for any, there exists a constant alpha such that if the difference between x plus h and x, which is h, is sufficiently small, is less than alpha, then the distance between their images is less than epsilon. Okay, so this is the continuity condition at the point x, and we shall see now that alpha cannot be chosen uniformly. It really depends on the point x. Okay, so this is just I'm saying that the distance between x plus h and x, if the distance between x plus h and x is less than alpha norm, then the distance between their images is less than epsilon. Okay, and here's the formula for alpha. Okay, now you'll understand where does it come from. It's not difficult to see because the estimation that we'll do lead us to this formula. So I take alpha to be the minimum, the smallest between 1 and epsilon over m. M actually is the constant in condition 3. Okay, this time. So m is a constant. So epsilon over m times the norm of x1 plus the norm of x2 plus 1. So we see here, so alpha really depends on x, on x1, x2, so on x. It cannot be chosen uniformly. Okay, unlike the linear, the case of one variable. So I'll prove this condition with this alpha. Okay, now it's very easy. Okay, so pick an increment h1, h2 whose norm in the product, which is the maximum, is less than alpha, and take another increment whose first component is 0. Okay, and now we do this triangle inequality. The norm, there should not be this vertex. So the norm of L of x plus h minus, so the distance between L of x plus h minus L of x in norm, I just apply the triangle inequality. So I add and subtract L of x plus k. And now I need to estimate each term in this sum. Okay, now look at the first term, L of x plus h minus L of x plus k, and just write them in components. So x1 plus h1, x2 plus h2, minus, now x plus k is just x1, 0, x1 plus 0, x2 plus h2, because the first component of k is 0. Okay, and now we use the linearity with respect to the first variable. So the second variable is fixed. It's x2 plus h2. When I do the difference, I get x1 plus h1 minus x1, which is just h1. So this is just linearity with respect to the first variable. Okay, now the second term, do the same thing, and I use the linearity with respect to the second variable. Okay, and I get L of x1 h2. Now I take the norms. Okay, if we take the norm of the first one, okay, so it's the norm of L h1 x2 plus h2, but we have condition 3. So a norm, this is less than the constant m times the norm of the first component times the norm of the second component. This is condition 6. And I apply also the same condition for this, the norm of the second term. So the norm of this is less than the constant times the norm of the first component plus the norm of the second component. And now I put everything together. So first, I apply the triangle inequality to this term. So the norm of the sum is less than the norm of x2 plus the norm of h2. First thing, this is the triangle inequality. So I didn't change the other. And now I use the fact that the norm of h of the couple h is less than 1 or equal to 1, but norm of h is the maximum between h1 and h2. So this term here is less than 1. Okay. And I didn't touch the other thing. And now I use the fact that both h1 and h2 in norm are less than the norm of h. So I get, so the first term will be, this should have been less or equal, not equal, because, so this is, the first term is less than m norm of h times this constant. And the second term is also less than m times the norm of x1 times the norm of h. So this is less or equal. And now I factor by m times norm of h. Okay, so I get what? I get norm of x1, x2 plus 1 plus norm of x1. And this is where the constant comes from. And now, by my choice of alpha, if norm of h is less than alpha, so it's less than epsilon over this quantity. So this quantity times h is less than epsilon. And that's it. Okay, now you understand where this formula for alpha comes from. So when searching for this alpha, we start by doing these estimates, and then we arrive at something. Okay, and then we can reason backward if you like. So there's no mystery. Okay, so suppose that you don't know what is alpha, and you now want to do this. So you can easily do these estimates because this is just linearity and triangle inequality. So when you arrive at this, you say, well, I used here the fact that now 1 is not really important. You can have put 2 here if you like. Okay, it's just a constant. So we have to take h in norm less than 1 in order to put a constant here, because this constant should not depend on h. Okay, the alpha should not depend on h. So I have to take norm of h less than 1 or less than a constant, let us say, and then I have to make this less than epsilon. Okay, so the norm of h should be less than epsilon over this quantity. And then I take the minimum. So there's no mystery. Okay. So this concludes the proof that 6 implies 1 and concludes the proof of the proposition. So now we have several equivalent conditions to the continuity. One of them is being the boundedness over bounded sets. And so continuous bilinear maps are also called bounded bilinear maps. Okay, and bounded because they map bounded sets into bounded sets, or they are bounded on the bounded sets, same thing. And the set of bilinear bounded maps from the product of two normal spaces into F is denoted by calligraphic L of E1, comma E2, semicolon F, this is just a notation, or B of E1, E2, F. So B for bounded. And so this is, as you may check, a vector space, because we can define the sum of two bilinear maps. It's a bilinear map, and a multiple of a bilinear map is, so this space actually is a vector space. It's very easy to check. And now I put a norm on this space, as we did for the case of linear bounded maps. The norm of a bilinear map is just the supremum over the unit ball, but here is the unit ball in the product. Okay, so this is the maximum, the supremum of the norm of Lx when x varies in the closed unit ball. And so it's easy to prove now, as in the case of one variable, that this is really a norm. And now I'll give some other characterizations of this norm. Now, as a particular case, if E1 equal E2, then we write L2 of EF instead of LEEF. Okay, so just economy of notation. So this is the set of bilinear bounded maps from E1 times E1 into F. So the two variables belong to the same space. And this will be the main case of bilinear maps that we shall deal with in this course. And as we did for linear bounded maps of one variable, the norm of L can be taken to be the supremum over the unit sphere, or the supremum over the open unit ball, and also the best constant in this estimate. Okay, and so same thing, can prove that. And the infimum here is actually a minimum, okay, because the norm of Lx is less or equal than the norm of L times norm of x1, norm of x2. So x here is the couple x1, x2. So same remark for the case of, as in the case of linear bound operators of one map, of one variable. So the supremum in the definition need not be achieved, so it's not really a maximum, not necessary, could be actually, but not necessarily. But the norm is the best constant here, so it's a minimum. Okay, you can prove this as an exercise. Now, examples of bilinear bounded maps. So we take E and F to be the space of continuous functions on a compact interval AB, and we equip it with the norm of uniform convergence, which is the same as the sup norm, the infinity norm that you know. And we set for UV in the space, we take L of UV to be the product. So we encountered it before. And now we know that this is bilinear, but not linear, once again. And the norm of L, as you may check, is equal to 1. Okay, prove this as an exercise. So we have how to prove that double inequality. So we have to prove first that norm of L is less than 1 or equal, and then norm of L is bigger or equal than 1. Actually, here the maximum is achieved, the supremum is achieved, because you can just take the constant functions u equal 1, v equal 1. Okay, so it's not a big deal. It's not always easy to compute the norm of a linear map, of a bilinear map. Okay, and more generally, if we fix a continuous function phi, and we consider the operator of multiplication against phi, then this is also bilinear, and it's bounded as well. And as you may check, the norm of L is equal to the supremum norm of phi. Okay, so here again, double inequality. But if you take u equal v equal 1, which are in the unit sphere, you get norm of L is bigger or equal than phi. To prove that norm of L is bigger or equal than the absolute value of phi of x, let's say, we have to take now u equal 1, v equal minus 1, and then you will get minus phi. So we get absolute of phi is less or equal to the norm of L, and since this is true for every x, so you do the and now another operator, the operator of derivation, of integration, sorry. So we take, if you have two, so take the same space, continuous maps, and we consider if you have two continuous functions u and v, we define a new map, their image under L is the antiderivative of phi uv, which vanishes at a. So it's an integral. But this is not a number, this is a function actually. So L now is a bilinear map from E times E into E. We encountered this before, but we just had one variable. So here we have two variables. So this is bilinear bounded, and you may prove, if you use the same arguments that in the previous video, that the norm of L in the space is just the norm 1 of phi, which is the integral from a to b of absolute value of phi of t. not totally trivial, because you have here once again you have to prove a double inequality. So, and a last example, an example of the derivation operator. So we just take E1 equal E2 equals C1, the space of continuously differentiable functions on A, B, and F, and we equip E1 and E2 with the norm that you already encountered, the sup norm of U plus the sup norm of the derivative, and we equip F with the sup norm. And now we fix phi in C1 of AB and consider the derivative of phi UV. Okay, so this is as easily checked to be a bilinear map, but it's not linear once again. So it maps E1 times E2 into F, because the derivative of a C1 function is C, and it's bounded as well. So it's bilinear and bounded. And I didn't try to compute actually the norm of L. You can do it if you like. Just first try, if you want to compute the norm of L, start by taking phi equal 1 to see what's happening. Okay. Okay, so these are fundamental examples of bilinear bounded maps. Of course, if you take, for example, L of UV to be the integral from A to B, then this would just be a number. Then you get a bilinear map that takes values into R. So the same examples of the previous video can be adapted here. Okay, and now the second main result of this video is the identification between two spaces of functions. So just one notation. If you have in general a function of two variables between sets, okay, then if we fix x in the first space and then the second variable, we get what we call a partial map with respect to the second variable. So we have a collection of maps actually when x varies. Okay, and so this is just the notation of the partial map. Okay, so f of x dot is the map from y to z that to each y associates f of xy. And similarly, I can define f of dot y. So this notation is widespread in analysis. Okay, and now here's the problem. Suppose that I have two normal spaces E and F, and I have a linear bounded map from E into the space of linear bounded maps from E to F. So for each x in E, L of x is not an element of F, but it's itself another linear bounded maps from. So actually, if I fix x in E, L of x will take value in L of E and F. So L of x is an element, is a function actually, from E to F. So I can apply it to an element y in E. And then I get, so there's no E here. Sorry, yeah. So they should be separated. So for every y in E, L of x evaluated at y is an element of F. Okay, this is very important actually, because when we shall define derivatives, we will encounter such maps that takes values in a space of maps. Okay, so we can consider L actually as a function of two variables. The first variable is in X, the second in E, the second variable is also in E, and the result will be in F. So such map can be identified with the map of two variables, and linearity of, we have double linearity here actually, because the first L is linear, the second L is linear. So actually we can think that L, so this expression L of xy is actually linear in x and linear in y. Okay, so it's bilinear actually, but not linear in the couple. Okay, because we have two L here. The linearity in x comes from this L, and the linearity with respect to y comes from this L. And okay, so we can identify an element in this space with a bilinear map from E times E into F. Okay, this is the idea behind the identification result that I will state now. Okay, in a more precise way. Okay, so consider two norm spaces E and F and equip the product with the norm, the maximum norm. Okay, now then actually this space of linear maps from E that take value in the space of linear bounded maps from E to F is isometric to the space of bilinear bounded maps from E times E into F. Okay? So an isometry is given by this operator, capital phi, between these two spaces. To each element here, call it L, associates an element in this space that I call phi of L. But an element in this space is really what? A map from E times E into F. That to each couple xy associates what? L of x, which is an element in LEF, evaluated at y, which is now an element of F. Okay, this is the idea that I was trying to explain. So it's easy now to check that phi is linear in L. So just try to estimate phi of L1 plus L2, phi of alpha L. It's very straightforward actually, because everything is linear here. Okay, so it's well defined. So it means well defined means that phi of L really is here. Okay, and you see that this is really a bilinear map in X and Y because of the double linearity. Okay, and boundedness. Now we will talk about boundedness. So it's well defined, linear, and bijective. And the inverse is given by this map, psi, that I call psi. So psi is phi minus 1. So it's the inverse operator. So to each bilinear bounded map T, we associate psi of T, which is an element here. An element here, as we said, is a map from E into L of E and F that to each x in E associates the partial map Tx dot. So Tx dot is not an element in F, it's an element in L of E and F. So when I put y, then if y is in E, then T of xy will be in F. So this is the partial map that we talked about. So this is pretty straightforward actually. And now we just have to check that phi conserves the norm. And this is just follows from the definition. But I have to warn you that if we take another norm on E times E, we don't necessarily have an isometry. We may have just an isomorphism. Okay, so it's important to take this maximum norm as we shall see now. Okay, in order to obtain an isometry. But actually, an isomorphism is also good. So if we take another equivalent norm here, we'll just get an isomorphism, which is fine in order to identify this space with this space. Now, why we do that? Because it's easier to work in this space, because this is just the space of maps of two variables. Okay, so it's a little bit easier to, more convenient actually, to work in this space than in this space. Now, why phi conserves the norm? Just to go back to the definition, the norm of phi L, just got phi. So the norm of phi L is the norm of this bilinear map. And the norm of the bilinear map is the supremum, as we said, over the unit sphere, the unit closed ball. We can take the sphere as well, of phi L of xy, which is just this. Okay, and here I'm taking the maximum norm. So when I say that norm of the couple xy is less or equal than 1, it means that both norm of x and norm of y are less or equal than 1. So this is the supremum over the product of the two unit poles. Now, as you may easily check if you go back to the definition of the supremum, so the supremum over a product or the supremum over two independent variables is the supremum of the supremum. Okay, this can prove this in more generality. If you have a function of two variables and the supremum over both variables varying in a product is the supremum of the supremum. I can also interchange. Okay, It's not difficult to see that. Double inequality, if you like. So the supremum over the unit ball in the product space is the supremum of the supremum. Now, if you look at the first supremum, this is what? This is actually the norm of Lx, because Lx, recall that Lx is a linear bounded map from E to F. Okay, so by definition, the inner supremum is just the norm of Lx. And now the supremum of the norm of Lx on the closed unit ball is just the norm of L. So phi conserves the norm, and therefore phi is an isometry. Of course, as you observe, if phi is an isometry and is a bijection, then the inverse is also an isometry. Okay, so this concludes the part on bilinear operators. And if you understood well this material, we can move to the more general case of multilinear maps or operators. Okay, so instead of just taking the product of two spaces, I take the product of an arbitrary number of them. So a multilinear map is a map of n variables. Of course, everything should be a vector space in order to talk about linearity, which is linear in each variable separately. Okay, so same definition. I will not give examples. And now the characterization of continuity is given by an analog of proposition 1.11. So a multilinear map is so of course we take just the same notation. So we take on the product the maximum norm, and we have an equivalence between the 6 conditions. So continuity everywhere at every point, continuity at the origin, which is 0, 0, 0, 0. Boundedness on the bounded sets, boundedness on the unit ball, boundedness on the unit sphere, and this important inequality that L of an n tuple in norm is less than a constant times the product of the norm of each component. Okay, so the product of E1, E2, En can write it in this way or in this more compact way. So it's exactly the same proof. You can just adapt it, copy paste if you like, but the notation are a little bit more cumbersome, but you can do it. So I will not repeat the proof here, exactly the same. And the last result, so same thing. So multilinear continuous or multilinear bounded is the same thing because of condition 3. And now the space of linear bounded maps with n variables is denoted by the same symbol, L of E1, E2, En, semicolon F, or B E1, E2, En, semicolon F. Okay, and same notation. Now I'll talk about the notation. And sorry, this is multilinear for it. So we take the same definition of the norm. So this is a vector space because the sum of two multilinear maps is a multilinear map. So it's a vector space, and on this vector space we can put this norm, same thing. So here x is a n tuple, so it's a vector x1, x2, etc. And when if E1 equal E2 equal En is the same space E, we write Ln of EF instead of LEEEEF n times. So this is the space of multilinear bounded maps with n variables, each variable belonging to. And for the definition of the norm, we have the same remark. We can take, so L is the supremum over the unit sphere of the product or the open unit ball, and it's the best constant here. So exactly the same thing, so just copy paste. And the last result is that if we have two norm spaces E and F, and we equip the product E times E times E n times with the maximum norm, then the space, this is what? This is the space of multilinear maps with n variables in E that takes values in another space, in the space of multilinear maps with m variables defined on E that takes values in F. So same thing actually. So this is isometric to the space of multilinear maps with n plus m variables from E to F. So the proof is just a copy-paste, but we just have to pay attention. The notation could be a little bit hard to write, but the same idea. So what is phi? Phi is this map from the first space into the second one. That to each element L. In element L, as we said, okay, is a multilinear map with n variables. So L of x1, etc., xn. If x1, xn belong to E, then L of x1, etc., xn takes values in Lm. So it's a function of m variables that I can denote by xn plus 1 up to xn plus 1. And so we define phi of L. So phi of L is now a function of n plus m variables. So the image, the phi of L evaluated at this n plus m variables, what do we do? Is very easy. We take the first n components, we evaluate L at the first n components, so we get an element here, and then we evaluate the result at the remaining m components. So it's very easy. So same structure as before. So in the case of a bilinear map, we just had L of x here and y here. So then we may easily check that phi is well-defined, linear, bijective, and the inverse is just an evaluation map. So if you have an element t here now, it's a function of, so if t is here, it's a function of m plus m variables. Its image is here, so it's an element here. So when we evaluated at the first n variables, the result is an element here, so it's a function of m variables. Okay, so phi minus 1 of t evaluated at the first at this vector actually is a map now, because I put a dot here, so it's a partial map. Okay, so the same structure, but now instead of x I have x1, xn, and instead of xn plus 1, xn plus m, I have of y I have this m variables. Okay, so to prove that phi conserves the norm, we just proceed as in the proof of theorem 1.4, and we see that the norm of phi L is the norm of L. Okay, so now if you just, it's enough to understand the case of bilinear bounded maps, because this is the most important case that we shall deal with. Okay, so this concludes this video about section 1.3 about multilinear bounded maps. In the next video, I'm going to do a very short review on Hilbert spaces that you shall need, and we will conclude chapter 1. Okay, so thank you for your attention and see you next time.